Hi, welcome to this tutorial on strain transformation and strain gauge Rosette. My name is Timo McGeehan, a mechanical engineering student at Arizona State University. Let's get started. First, let's discuss what is a strain gauge. A strain gauge is a device used to calculate the strains and stresses experienced by a material. But how do the strain gauges work? Well, a strain gauge is a conductive piece of metal that when stretched increases in length and decreases in cross-sectional area. This change in cross-sectional area and increase in length increases the resistance of the metal. This increase in the resistance of the metal is then turned into a voltage increase, which is measured. This measured voltage change indicates to us that strain is occurring in the material. But how are strain gauges used? Strain gauges can be oriented in many different ways to optimize calculation of stress or strain or Young's modulus or shear modulus. Here are several of the orientations often used by strain gauges. As we see here, the strain gauge C is oriented 45 degrees from the x-axis. The strain gauge B is oriented in a parallel relation to the x-axis, and the strain gauge A is also 45 degrees in relation to the x-axis. Here are some other orientations of strain gauges. As we discussed, these different orientations of the strain gauges allow for scientists and engineers to measure different properties of the material in different ways. Another way strain gauges are used is in the experimental study of materials. In this setup here, we see a force, a measured force that is, being applied at the end of a torsion arm, which induces strains and stresses in the material or the bending arm. This material is situated with strain gauges at various orientations. As we see here, the strain gauge 2 is oriented 45 degrees to the strain gauge 1, which is parallel to the y-axis. The strain gauge 1 and strain gauge 3 are parallel to the x-axis, and the strain gauge 2 is oriented 45 degrees to that x-axis. Using the measured force, torque, and bending theory, as well as the strain gauge data, one can calculate the Young's modulus as well as the shear modulus. But before we can understand how to obtain material properties from the strain gauges, we must also understand how strain transformation works. Strain transformation helps us to determine what the stress and strain state of a material is after it has undergone deformation. Take, for instance, this infinitesimal block situated along the y and x plane. This is its initial state, with an infinitesimally small length of dy along the y-axis and an infinitesimally small distance dx along the x-axis. Now, let's deform this body. Now the body is deformed. This is the deformed state. To calculate the strains experienced by the object, we measure the distance changed along the y-axis, as well as the distance change along the x-axis. This is called the normal strain, which, as shown here, is the infinitesimal length of dx plus the strain in the x times dx, as well as the infinitesimal value of dy plus the strain in y times the infinitesimal length of dy. This is the normal strain. Another property of the deformed state is the degree of deformation between the original axes and that of the deformed state. This is the shear strain, indicated by epsilon xy over 2. Now, let's look at this transformed state and figure out what the strain in the x, the strain in the y, and the shear strain is in this new deformed state. Using trigonometry and equations of equilibrium, one can derive the strain transformation equations. Now that we have derived the strain transformation equations, we can begin to implement the knowledge we have of strain gauges, as well as these numerical analytical methods to calculate how a material changes from one state to another. Let's look at an example. In this example, the 60-degree strain rosette is mounted around a point on a beam. The following readings are obtained from each gauge. The epsilon A equals 100 times 10 to the negative 6. Epsilon B equals negative 350 times 10 to the negative 6. And epsilon C is equal to 250 times 10 to the negative 6th. As you see, none of these values have units because strain is just a change in distance over distance, or meters over meters in metric, which is unitless. The question asks us to determine the in-plane principal strains. After doing so, it asks us if a small line segment is placed close to the point and has initial undeformed vertical length 10 millimeters, estimate its new vertical length after it has been mounted on the beam as shown. Let's get to solving this. These are the strain transformation equations we derived earlier in this tutorial. Taking the strain transformation in relation to the x-axis, we can figure out the strains along the x, y, and gamma xy shear strain values. Let's start by looking at the original orientation again. From this original picture, we can see that strain gauge A is situated 120 degrees from the defined x-axis, which is pointing in the left. The strain gauge B is situated 60 degrees from the x-axis, and the strain gauge C is situated 0 degrees from the x-axis and is parallel to the x-axis. Given the original values from the problem statement for the strain gauge data acquired for strain gauge A, strain gauge B, and strain gauge C, as well as the data derived from the picture as we calculated the degree measurements from the x-axis, we can now, using the equation for strain in relation to the x-axis, input all of this information to calculate the strain in x, strain in y, and the gamma xy, which is the shear strain. Below is the data combined into the strain transformation equation. As we see here, strain gauge A, which had a degree value of 120, is inputted into the equation as 2 theta. So cosine 240 is the resulting value, and sine 240 is the other resulting value for degrees. Similarly, we can see how strain gauge B, with its 60-degree orientation, is inputted into the equation, giving us the cosine 120 and sine 120 values. And likewise, the strain gauge C, with its 0-degree orientation, giving us the cosine 0 and sine 0 values. We can now combine this equation, separate the fractions into simpler forms to make it easier to calculate for us. Seen below, we separated strain in the x over 2, that value, strain in the y over 2, strain in the x over 2 times cosine 240, minus strain in the y over 2 times cosine 240, as well as the gamma xy over 2 sine 240. All of this for strain gauge A. Similarly, a process was taken to separate the strain gauge B components from their fractional form. This gives us the below equations. Now, given the below equations, we can simplify even further by combining the like terms of epsilon x, epsilon y, and gamma xy. Here is the equation with each of the like terms combined. As we see here, epsilon x is now multiplied by 1/2 plus cosine 240 over 2. Epsilon y is multiplied by 1/2 minus cosine 240 over 2. And gamma xy is now multiplied by sine 240 over 2. Those are the values for strain gauge A. Likewise, a similar process can be implemented to derive the equation seen for strain gauge B, just with different degrees of 120. Similarly, strain gauge C is separated and combined with its like terms to derive the equation seen below. Now that we have combined the like terms, let's calculate the trigonometric values we have for strain gauge A, strain gauge B, and strain gauge C. In strain gauge A, we have a trigonometric value of cosine 240, which, when inputted into the calculator, gives us a value of negative 0.5. Another trigonometric value in the strain gauge A equation is sine 240, which when implemented into the calculator, put into the calculator, gives us approximately negative 0.866. Now let's move to strain gauge B. Cosine 120, when inputted into the calculator, gives us negative 0.5. Sine 120, when inputted in the calculator, gives us approximately 0.866. Now, for strain gauge C. Cosine 0, as we know, is just 1, and sine of 0 is just 0. With these trigonometric values, we can now simplify even further the above equation. Here is the most simplified form of the strain equations for strain gauge A, strain gauge B, and strain gauge C. These equations can now be put into a matrix to solve for the strain in X, the strain in Y, as well as the shear strain in XY. Here again are those equations. Now let's put them in their matrix form. As we see, 0.25 is in the upper left hand corner, 0.75 is in the middle, and negative 0.433 is in that right corner. Oh, I'm sorry. Okay, now that they're in matrix form, we can now solve this matrix in a calculator. Now we can obtain the strain, the normal strain that is, in X, the normal strain in Y, as well as the shear strain in XY. These values are 2.5 times 10 to the negative 4th for shear strain in X, or for normal strain in X, negative 2.5 times 10 to the negative 4th for normal strain in Y, and negative 5.196 times 10 to the negative 4th for shear strain in XY. Using the in-plane strain equations, we can now calculate using the in-plane principal strain equation, we can now calculate what those principal strains are, because we have values for epsilon x, epsilon y, and gamma xy. Here are those values again. Let's input these calculated strain values into the in-plane principal strain equations. Here are the values of epsilon x, epsilon y, and gamma xy inputted into the in-plane principal strain equation. equations. As you can see from the equations, we will obtain two answers. Here again is that equation. The two answers that you calculate turn out to be 3.605 times 10 to the negative fourth and negative 3.605 times 10 to the negative fourth. And when you look at the equation, you can see that this makes sense, as the first value in the equation will always be 0, regardless of the plus minus sign. And the values underneath the square root will also remain the same. Thus, the principal strain values we obtain make sense. This is the answer for part 1. Now, let's move on to part 2. The small line segment is placed close to the point and has initial underformed vertical length 10 millimeters. Estimate its new vertical length after it has been mounted on the beam as shown. Okay, as we remember, this normal strain calculated along the x was 2.5 times 10 to the negative fourth. Normal strain along the y was negative 2.5 times 10 to the negative fourth. And the shear strain along the xy was negative 5.196 times 10 to the negative fourth. Now, as you probably remember from your mechanics classes, either 212 or 213, strain is the change in length over the original length, or L final minus L initial over L initial. We can use this equation as well as the known value of strain in the vertical direction, or the y, to calculate the final length. By reworking the positions of the different values with algebra, we can now obtain a value for the final length of the segment. And this is 9.9975 millimeters, which makes sense given that the normal strain along the y direction was a negative value, meaning instead of being stretched, the small line segment was actually compressed. This is the answer for part 2. And that concludes our tutorial on strain transformation and strain rosettes. Thanks for watching, everyone.